That's true, but there's a good reason to restrict ourselves to Earth-like systems when we do these calculations of the abundance of life-bearing worlds. It's because we're trying to find the most conservative number for possible origins of life to help explain the Fermi paradox. We want to find out even if the most conservative estimate still gives us a large number, because that tells us that we need to do work to look for other things to explain the absence of evidence for technological life. Some of you pointed out other possible explanations for the Fermi paradox and the specialness of Earth. Lucas Nicholson and others remind us that the Earth's moon is exceptionally large, and such large moons are probably very rare even if Earth-mass planets are common. Our large moon has been proposed as an important factor in the appearance of life, which may have first appeared in tidal pools. The tidal pool hypothesis is no longer the clear frontrunner for abiogenesis. For example, geothermal vents on the ocean floor are looking like a good option for the origin of life, and they don't care about the moon. These are also found on gas giant moons, so that boosts our potential abiogenesis location number quite a bit. John Thatcher told us about another idea that I hadn't heard of, that the late heavy bombardment may have been needed to seed the surface of the planet with a high abundance of heavy elements, which was perhaps necessary to get life started. The late heavy bombardment was a massive meteor shower that lasted millions of years, and probably isn't something experienced by most terrestrial planets. On the other hand, some scientists doubt that the late heavy bombardment even happened. All of the evidence is from cratering on the moon, and biases in the analysis of that data may have led to miscalculations of the bombardment rate. Okay, onto the expanding universe stuff. Snufkin Matt asks, if space doesn't expand inside a gravitational field, then what happens at the boundary between this, where the space is expanding? Would the expanding space try to drag neighbouring space with it, and would you get a kind of tug of war between the two? Well, yes and no. First, assuming no cosmological constant and dark energy, the expansion of the universe does not continue to tug on the space within gravitationally bound regions. However, those bound regions fell together from matter that was initially moving apart in the expanding universe, and that kinetic energy affects the final form of the bound system. So I would think galaxies that formed in an expanding universe would be more puffed up than those that formed in a static universe. Nathaniel Cleland responded to that comment to address the dark energy issue. He rightly points out that the Schwarzschild metric isn't really valid in a universe with a cosmological constant. There would indeed be an initial effect due to the tiny vacuum energy inside the galaxy. However, that effect is minuscule and couldn't really be characterized as a tug of war. It would result in a very, very slightly larger size to the Milky Way than without dark energy. Eric Marsh asks if space inside gravitationally bound systems actually contracts rather than simply not expanding with the rest of the universe. Well, the answer is kind of yes. You can interpret the math that way. There is a valid interpretation of general relativity in which we can say that space is flowing inward in a gravitational field. You may have heard me say that space flows across the event horizon of a black hole at the speed of light. That's the velocity of an inertial frame that falls from infinite distance towards the black hole. In the same way, an inertial frame at the cosmological event horizon is flowing away from us at the speed of light. Evelyn always tells people not to imagine intergalactic space as expanding, but rather that galaxies are shrinking. Jonathan Rose has a similar hypothesis that all matter is constantly shrinking within a static space. Listen guys, I understand that as smart, science-educated people, it's extremely tempting to make up almost plausible nonsense to fool the common folk. Believe me, I feel the temptation as powerfully as anyone. But neurological studies have shown that people who accept or propagate science misinformation are 50% more likely to suffer from degenerative microcephaly in later years. In other words, everyone's brain shrinks like those galaxies. I think I can feel it happening to me right now.
If you used every particle in the observable universe to solve the Schrödinger equation and do a full quantum simulation of some chunk of the universe, how big would that chunk be? Would it be a solar system, a planet, a cat? It would be, at best, a large molecule. That's how insanely information dense the quantum wave function really is. And yet we routinely simulate systems with thousands or even millions of particles. How? By cheating. Let's learn how to cheat the universe. Quantum mechanics allows us to predict the behavior of the subatomic world with truly incredible precision. For example, let's say you want to know the intricate behavior of an electron, whether it's bouncing around inside a box or part of a hydrogen atom or moving through a double-slit experiment. You just scratch the good old Schrödinger equation on the blackboard and solve it to learn the probability distribution of the electron locations or the energy levels of the system or whatever.